All right. Thanks, everyone, for coming back. I'm going to more or less start off from where I left off yesterday. That's at least for the first few minutes. I did manage to I wanted to show you one more construction of codes with all symbol locality. I decided it won't be fair to you if I don't show you this construction. So I'll finish that, and then we'll talk about something else. So let me just remind you, we're considering this notion of locality. We say that a linear code has locality R, all symbol locality R, if each coordinate is expressible as a linear combination of R other symbols. Which R other symbols depends on which coordinate you're trying to express. We were interested in this question of what are the trade-offs between rate distance and this new parameter called locality. And it turns out that you can get an exact bound here, which generalizes the singleton bound. And this is the shape of the bound. It tells you that you need a constant overhead for constant locality, and then what you expect for distance. Right? The proof is essentially an algorithmic proof. You know, it's the kind of proof which a computer scientist might like. Alternate proofs, Papailiopoulos and Dimakis, they basically redo the same proof, but instead of linear algebra, they use the language of information theory. They show that if you consider the total entropy in your symbols as opposed to the rank of your set, then the proof will go through. It will generalize even to nonlinear codes. Very different proof, at least it looks fairly different to me, using the theory of generalized Hamming weights was given in this work by Prakash et al. This might be a proof which would appeal more to a coding theorist. A graph theoretic proof was given by this work of Barg and Tamo. This is a proof which might appeal more to a combinatorialist, and you know, I look forward to the next proof. There's still some space here. Several generalizations of these kinds of codes with locality have been considered. I already mentioned nonlinear codes. You can talk about vector codes. Bring the alphabet size Q into the picture and ask what are the trade-offs once you also care about Q. And then this other interesting variant where right now we're just saying, in essence, we say that each coordinate is protected by something like a short parity check. You could ask for some more powerful local protection, like a short local MDS code around each coordinate, and people have looked at variants like this. And basically all the lower bounds and structure theorems, they more or less generalize in the way that you'd expect. On to explicit constructions of codes with all symbol locality, I showed you this nice construction of Silberstein et al. Based on Gabardine codes. It gives you the optimal length and all symbol locality, but the alphabet size was exponential in the block length. Another construction which I didn't talk about by Tamo, Papailiopoulos, and Dimakis also gives you the same properties, but again, Q is exponential in the encoding length K. For me, K and N, you know, I'm not going to distinguish too much between them. Lastly, let me show you this Barg and Tamo construction, which is going to be based on Reed-Solomon codes, and here we'll get linear alphabet size, linear in the block length. Okay. So the construction, it's basically like Reed-Solomon codes, except you don't take monomials of every degree. You take a very special set of degrees. So what is the degree set? Well, you take non-negative integers, but then you decide, okay, so let's fix the locality parameter R. Okay. So you take the degree set, you decide that you don't like integers that are congruent to R modulo R plus 1. Drop all those integers, and now you want a code of dimension K, so pick the first K integers where you keep dropping every number which is R modulo R plus 1. Right? So you can do this, and you'll basically terminate, at least I did this calculation last night, and this is where it ended. The largest number is of size K times 1 plus 1 over R minus 2. Ignore the minus 2. You're picking R out of every R plus 1 number, so this is what you should expect. Okay? And then the polynomials are just univariate polynomials with this degree set, evaluated at all points in FQ star. And now, just use the standard. If you want to bound the distance and the locality of this code, the distance bound will just be the standard bound for Reed-Solomon codes, that you have a polynomial of certain degree. It can have at most degree many zeros, so n minus degree many non-zeros. N minus this number, by sheer coincidence, happens to be that number I have written over here. You just do the move d over to the other side, you'll get n minus this quantity, and that's what you want. The more interesting thing is, why does this code have any locality at all? Because Reed-Solomon codes don't have any locality whatsoever. So actually, I haven't specified the code completely. You need to be a bit careful in how you choose the field size q. So let's assume that fq star contains a subgroup, a multiplicative subgroup of size r plus 1. It contains G subgroup of size r plus 1. So basically, all the elements in this subgroup G, they satisfy the property x raised to r plus 1 equals 1. And now you can partition fq star into cosets of this subgroup. Each coset is of the form A times G. So even elements here will satisfy a low degree equation, which is that you first divide by A and then you apply the same equation, right? So the coset A times G consists of all elements where x raised to r plus 1 is essentially A to the r plus 1. Okay. Okay. So now let me tell you what the groups of symbols are which have some locality property. They are exactly the partitions of fq star into cosets of G. Why is it local when you restrict to one of these cosets? When you're restricting to one of these cosets, in essence, you're taking this polynomial and you're quotienting it by the equation x raised to r plus 1 equals some constant, right? So everything is going to collapse to a polynomial of degree at most r. And now the holes in the degree sequence work to your advantage because you omitted all monomials which were r mod r plus 1. So actually, you don't have any terms of degree r. You only have terms of degree r minus 1. So restricted to these r plus 1 points, everything is a function of degree r. But these, when you restrict them to these r plus 1 points, you get a polynomial of degree r minus 1. So it's a non-trivial Reed-Solomon code which has distance 2. So there is some dual constraint on these which relates them together. Right? So that is why you get locality r. So, okay, so this was a little fast and furious, but it's a very simple and elegant construction. So what is the field size here? Well, and this is a very general construction. We worked with multiplicative subgroups. All you really need is to be able to partition your space of evaluation points into these small sets which satisfy some low degree equation, right? So it's a very general thing. It will comfortably give you alphabet size, field size, linear in the length of the code. All right. So, so one very important thing though. This construction had this much stronger property we saw last time, that when you puncture each of these local groups in one coordinate each, what you get is an MDS code. You could look at this code and wonder, does it have this property? And it's certainly not obvious to me. There might be a way to get it by doing something clever in addition, but if you just puncture this, right? Okay, what you're getting is a bunch of evaluation points in fq star. But now the space of polynomials, it's hard to argue that it's MDS because yes, it's univariate polynomials, but it's univariate polynomials of much higher degree than you expect, right? These are polynomials of degree 1 plus 1 over r times k. So it's not obviously an MDS code. All right. So you get a smaller field size here, but in comparison to, and I believe this other construction of Alex and his co-authors also has this stronger property that it can correct any such puncturing, right? So these things seem to require much larger field size. Do they really? This is going to be the focus of the rest of today's talk, right? Okay. But before I get there, let me just tell you some other work which people have done about, we have this very simple notion of locality. Could you have even stronger notions? So this is a very interesting topic, and I don't have time to cover it, but at least this will tell you where to look if you're interested in this. Like firstly, as I said, this notion of having regeneration and notion of having locality, these seem like very natural complementary notions. And people have asked, can we combine these and have codes with local regeneration? So these are the first couple of papers on this. There's probably more. This other variant I talked about, where your code actually has a short MDS code protecting each information symbol with distance better than 2, right? So again, this is interesting in practice because it allows for the following thing. Right now, if x1 is just protected by a parity check equation, when I'm serving a degraded read for x1, then I just need to read all these other R symbols and wait till all of them responds. But if x1 is protected by some kind of MDS code, I have a bit of flexibility here. I just ask all these nodes which participate in these MDS code, as soon as sufficiently many of them respond, I'm done, right? So now, okay, this raises a whole other set of questions like, what is the right way to set the threshold and so on. It seemed like an extremely natural question, which I was sure that someone would have addressed. And as it turns out, it has been addressed in this very recent paper by Kannan and his co-authors, where they analyze, how much of leeway do you want to avoid these bottlenecks. Another notion which has been studied is sequential local recovery. Here what happens is that many things fail. You are able to correct one erasure using just R reads. Okay. Now you're able to correct some other erasure. Maybe you couldn't have corrected this before using a further R reads. So you go on and completely locally, you finish your decoding. Right? So this is, again, I find it a very natural notion. For the computer scientists in the audience, none of these notions are exactly aligned with what we think of as locally decodable codes. As David pointed out last time, I haven't really defined what locally decodable codes are. I will shortly. Here is a notion which comes very close to it. They say that, okay, what is locality? It means there's a group of R other things that you can read to repair this node. Okay, how about if I have several disjoint groups, right? One reason this might be good for you is that now you can serve not just one read to this x1, but several parallel reads. You send the first person to read this group, send the second person to read the other group, and so on, right? So this notion was introduced, I believe, by Wang and Zhang, and further studied by Barg and Tamu. Here is the formulation of the problem, which comes very close to what we think of as locally decodable codes. So now, already from the rate distance trade-off, we know that the overhead you incur for distance is small as opposed to the overhead that you incur for locality, right? So in reality, you could say, I want to correct some D1 number of errors locally and D2 number of errors in all. Let's forget about D2. You can get that by adding D2 additional parity checks if you need to, right? So let's just formulate codes which can correct locally a certain larger number of errors than just one. So in particular, suppose I want an NK linear code where even after D arbitrary failures, every information symbol has locality R. Which means that D things failed. If somebody asks me for x1, let's say x1 is one of these failures. Now someone wants to read x1, I can still serve this request by reading R other things. What are the rate distance trade-offs for such a notion? And this, I claim, is essentially LDCs as computer scientists know them, just tuned to the model of erasures rather than errors, right? So if you have these D disjoint local recovery sets, then of course you get this notion, but you don't need them disjoint. It's basically the gap between vertex cover and maximum matching in hypergraphs. Okay? And to start towards proving a lower bound for this problem, this Barg-Tamu lower bound, which gets a nearly optimal lower bound for this disjoint parities model, it seems like a good starting point. Okay. All right. So now I'm actually done with the first part of my talk where we talked about locality. Now in the remaining time, I'm going to talk about reliability of these codes. So really, if you're designing codes for storage, certainly locality is a good property to have. Local regeneration is even better. But what kind of errors are you really trying to correct? If a code has a certain minimum distance, does that mean it's reliable enough? I'm going to try and convince you that actually you might want something stronger than just minimum distance, and then we'll talk about explicit constructions of such codes. Okay. All right. So what kind of failures actually happen when you're storing, data in these kind of huge data centers, right? So the thing which is very common here is correlated failures, which is a lot of machines will fail at the same time, but it's not like one machine from here, one machine from there, and so on. When these large correlated failures happen, it's usually for a reason that you could have anticipated. Like all of these are sharing the same power source that blew up, or they are sharing the same network switch and something happens, and so on. Like even more dramatically, you can imagine, and a lot of storage systems now do this, they have data centers in different geographic locations, and you could imagine that for some reason, like maybe a whole data center goes offline. Like let's imagine that you're storing data in Redmond, Boston, Mountain View, Cambridge, China, and India, and then one morning, suddenly, inexplicably, your whole center in Mountain View is gone. It sounds like a very, unlikely scenario, but stranger things are known to happen in practice. Right? So this is the problem here, that you can have these large correlated failures.
Got it. Took a while.
This time, if I get fired, I'll know exactly why.
You want to cut out that part?
I should be good about my citations. Like this example was suggested to me by Jayakumar. Right? So in addition to these, huge correlated failures, so you have these huge correlated failures, and then uncorrelated failures, it's fine to assume that these are independent. Okay? So here is a toy example that I'm going to think about. Say we have 4 racks of machines, and for some reason a whole rack could go offline. Okay? And you have about 6 machines per rack. Now this correlated failure model means that, let's say that the machines fail independently with some probability P, and rack failure is a much more unlikely event. Let's say it happens with probability something like P cubed. Okay? So this means that there are some 7 failure patterns, which come about by failing a rack and then one more machine, which are more likely even than 5 failure patterns. Okay? Just because, 5 failures could only happen from 5 independent failures, but 7 failures you could see because a rack failed and then one more machine failed. And actually this scenario is kind of very close to the kind of scenario that we were actually dealing with when we were designing codes for Azure storage. It's not so much a rack failure as they are taking a whole bunch of machines offline at a time for upgrading. This is when they are at their most vulnerable. So they want to be able to serve requests to the machines which are offline and also not lose data if there are more failures.
So, question.
Yeah.
So in wireless communication, what I used to work on, there's a lot of correlated failure due to fading of the channel. Mm-hmm. So the channel goes down for a while. The typical strategy of that is to interleave, is to break up the correlation so that you have independent failure again. Yeah. Could you not apply the same ideas here?
I think when you see the solution that I'm suggesting, it will look a lot like interleaving to you. Right? So what I'm going to suggest is like, look, this problem comes about because you insisted on your code having a certain layout. And you should account for this layout in the codes that you designed for this topology. And when I say, you'll see that it's basically the same idea, I guess, as interleaving, that the errors, if you have a lot of errors, they are well spread in a way that you can handle them. So yeah. Okay. So let's say that, so concretely, let's say in this scenario, we want to tolerate 1 rack failure and some 3 additional machine failures, right? The first thing you could try is to use a Reed-Solomon code with suitable parameters. Since in the worst case, we are gunning for 9 failures, and Reed-Solomon doesn't care which 9 nodes fail, you'd use a code which has minimum distance 10, right? Which would work fine, but the trouble with a layout like this is even 1 machine fails, then to serve a read to that machine, you're reading a ton of data, right? This is the original reason we said we want to do something different from Reed-Solomon codes. The other solution to do would be to use these LRCs that we saw last time, which were derived from Gabardine codes, right? So basically what you have is that each symbol here think of the topmost entry in each of these as a parity check of the symbols in that column, right? This code has the very nice property that you just puncture it. If you puncture any one row, what is left is an MDS code, which is exactly what we want. And in general, when one machine fails, you can serve it by just reading 3 other machines. Now, okay, here's the point I want to make. A single rack failure here leaves you with an 18-15-4 MDS code, but this is not something that you'll get just from thinking about the minimum distance, because the minimum distance of this code is 6. It's that the kind of failure patterns that you care about are exactly tuned to the kind of things that it can correct well, right? Okay. So, and also, it shouldn't surprise anyone that the codes we saw last time happened to solve this problem pretty well, because this is the problem we were trying to solve initially when we were starting to work on LRCs, right? But anyway, so the point is, how do you come up with a notion which captures things like this, that your code is good for the kind of failure patterns that are very likely to arise?
So maybe I wanted to make a remark. I'm thinking about it. So he wants to tolerate, relating to David's comment, he wants to tolerate any 9 failures, and there is, I guess, 24 choose 9 ways that you could fail, right?
No, not any 9.
Right. That's exactly the point. Right? So if you want to tolerate any 9, you have to go with Reed Solomon and lose.
Of course, yeah.
But now you say, well, not any 9 are possible, so I'll just design for the specific sets. Is that the same as interleaving? That's what I'm trying to think for.
Well, maybe in a vague sense that, when I think of interleaving,
the 9 sets of failures that you want to deal with and design the code only for those 9 sets that you care about. Whereas I guess...
So here, all I'm saying is that what this code is good at tolerating is error patterns which are spread across columns. The kind of 6 error patterns which will actually make this fail is when you concentrate all your errors, I basically take out x1, its parity, and everything in this column, right? So things which are concentrated on a few columns are hard. Things which are spread across many columns are easy. So in that sense, I guess there's a similarity to interleaving, is all I'm saying.
I think what in wireless, we usually don't use such huge alphabets and don't deal with erasures, right? So there, you interleave. You basically say, okay, my erasure is 24, but in reality, if the errors are random, I can actually correct, 40 errors. And interleaving just makes the errors look more isotropic, if you will.
I think the errors versus erasures is not really the main point. But the main point, I guess, is probably that if you just had the 9 random errors, you have a code that can tolerate 9 random errors, but you don't have a code that can tolerate 9 bursty, any 9. Yes. Yeah, but here we are doing, we will say, okay, if you want any 9, you'd pay with this Reed Solomon, but if you want specific sets of 9, I will design a code for the specific set. Yeah. So I guess it is a little different.
No,
because in the wireless case, it's
an MDS code. You interleave, you can correct any 9, right?
Sure, but he's not going to deal with any 9. Right? He's going to design the code for specific sets of 9. Okay. So it's
I think it's related, because if you interleave, then you're essentially saying you're only focusing on certain error patterns, right? Because you're assuming after you interleave, you get essentially independent errors.
So it's not quite that. So yeah. So maybe let's, I'll show you what we do, and then we'll talk more about whether, I'm not saying it's a very different idea. Maybe in the details it's slightly different, right? Okay. So I guess what we are going to say here, okay, so this code here, it gives you a stronger guarantee than minimum distance, which is that any row fails, you're left with an MDS code. Such codes, they have been studied before in the context of disk storage by Planck, Blom, and Hafner. They call these sector disk codes. In fact, the guarantee here is even stronger than any one row failing. It's one entry per column failing leaves you with an MDS code. Okay? Such codes have also been studied before, and these have been called partial MDS codes. So all of these are models which people doing disk storage, RAID kind of things, they not very different from us, I guess. They independently said these specific topologies are interesting to us. Right? Okay. So what this notion of maximally recoverable codes, it basically tries to say that, look, if correlated failures happen, we have good information about what things are likely to fail as a correlated thing. So presumably in designing your code, you're already taking this into account, right? So your code has a certain topology. which accounts for the kind of failures that are very likely. And then your code should be as good as possible given this topology. And the motivating example really is Reed-Solomon codes, where if you have a certain number of erasures and you have those many equations, then you can correct it. We want something similar here. We see a certain erasure pattern. If we have the right number of linear equations to correct these, which we have for these well spread out error patterns, we should be able to correct these erasures. That's all that's going on. Okay. So to set this up formally, we're going to talk about codes with a prescribed topology. Topology is a fancy name for something fairly simple. You have some variables, alpha 1 through alpha t. These are the things that as a code designer you get to choose. Right? And then the topology is basically given by a parity check matrix where each entry now, it could be a constant or it could be a linear function in the alpha i's. I could say affine function in the alpha i's and capture both of these things. Right? So what does this do? It basically encodes things like locality constraints, that I want this to be a local parity check on this group, or I want something else to be a sum of some other things which could include both data and parity symbols. It allows you to express constraints like that. Now, to instantiate a code of this topology, you just pick the alphas, and you want a good choice of alphas. As long as I said, if you have enough equations, you should be able to solve an erasure pattern. Which is, you want a code. We say that a code is maximally recoverable if it corrects every error pattern that is possible. So you have a certain set of erasures. Think of these as variables. You have certain equations in these variables. If these equations don't even have the desired rank, then you're lost. But assuming that they have the desired rank, you should be able to solve them. So you.
What is your allowed patterns?
Anything, yeah, I'm going to say that more precisely here. So I have this parity check matrix where each entry is a linear function in the alphas. Now, somebody comes up with an erasure pattern, right? And we say, okay, these are the variables. These are all the equations I have in these variables. Are these enough linearly independent equations? Just thinking of these as formal linear polynomials. And if so one thing, the obvious necessary condition is that you need enough linearly independent equations. If you have that, I want to be able to correct this pattern. So formally, this would come down to saying that a certain determinant is non-singular as a formal polynomial, or that if somebody somewhere is able to find some choice of alphas for which this erasure pattern is correctable, I want my code to be at least that good. This is one choice of alphas which is as good as every other choice of alphas possible. It corrects anything that you could correct by plugging in alphas here. Okay, so this is, this is a very strong, and we're just trying to come up with a clean definition here. Let's do some concrete examples to see what this would translate to. Firstly, it's good to know that such things exist, and we have concrete examples of them. So MDS codes would fit this definition. So what is an MDS code? You just have H global equations on all the variables, and each coefficient in an equation is an independent variable you get to pick. And if you choose these according to the Reed-Solomon parity check matrix, then it's maximally recoverable because anytime you have enough equations, you can invert the matrix. A more interesting example is the one that we were talking about earlier of LRCs. Now, again, here I'm going to make a few divisibility assumptions, which I want to sweep under the carpet. I'll assume R divides K, R plus 1 divides code length, and so on. We want codes where there are two kinds of constraints. There are these local constraints which say the parity of each column sums to 0. In addition to these local constraints, you get to throw in H global constraints on all the symbols. These are just equations which you decide what coefficients you want there. Okay? And by the lower bound we saw in the last lecture, if you want an LRC of optimal length, right, this topology is more or less canonical. Okay, the distinction I'm trying to make is this. You can only talk about maximally recoverable codes once you fix a topology. LRCs, as I defined them, just give you some locality property. There's no talk of topology in the definition of LRCs themselves. But the proof which we saw actually said that if you want an LRC which gives you optimal length and locality for every symbol, then the topology gets fixed. Okay? So it's kosher to talk about a maximally recoverable LRC because with the right divisibility restrictions, there is a fixed topology. It's this one. So when is a code with this topology maximally recoverable? Well, here maximal recoverability is exactly what we've seen before. Puncturing 1 in each column leaves an MDS code. Right? The effect of puncturing 1 in each column, in effect, should be to just get rid of these locality constraints. And what you left behind should be an MDS code. So here, okay, and SD is, maybe let me not say more about that. Here, the bottom line is that we know constructions, but they require fairly large field sizes. I'd like to contrast this with maximally recoverable tensor product codes. What is the topology here? I've used the same picture, so it looks very similar, but on one hand, you have these column parity constraints, and then you have H constraints on each row. These are not truly global constraints, they are constraints on a row. So certainly, if you choose these as well as you can, what you're going to see within a row is an MDS code, and then the columns satisfy a parity check equation. Okay? So when is such a code maximally recoverable? Well, the answer is that we don't really know. We don't have a clean characterization of what error patterns you should be able to correct using such a code. The one thing we do know, which comes as something of a surprise to me, is that it's not sufficient that each row code, the row codes are all the same so that this actually makes sense as a tensor product. Okay? It's not sufficient that the row code just be MDS. That is necessary, obviously. It's not sufficient. There are examples, very small examples, where tensoring a Reed-Solomon with parity check is not maximally recoverable. So where might such a setting come up, right? So imagine that currently you just have one data center. There you're using Reed-Solomon codes. Then tomorrow you decide you want to use 4 data centers. The most natural thing is to have just Reed-Solomon locally within each data center and do some simple XOR across data centers. This is exactly the code you'll have. And I believe Facebook has written a paper saying this is exactly the code they have, Reed-Solomon tensor with parity. So why Reed-Solomon? Maybe there are better codes, MDS codes that you could be using.
So, Parikshit,
yes.
Maximal recoverability is there if you think of some sort of bipartite graph?
Very good, yes. There is. So Venkat is making this very good point. So if the topology, if there's no locality among the parity checks, then you can think of this nice bipartite graph that you're talking about. The left-hand side is the nodes. The right-hand side is which parity checks read which nodes. Now Hall's theorem will give you a nice characterization. But in this case, we have some locality among the parity checks themselves. And that is the first place where this breaks. It's not clear what things should be correctable. Yeah, so sorry, I should mention that this notion of locality was introduced in this paper by Chen, Huang, and Li in 2006 or so. And there they made this, they proved this, that for the setting that you're talking about, there is an exact characterization of when something is correctable. We want to generalize it to allow things like locality for all symbols, basically. And now it's not clear what the characterization is.
Missing something about the definition. So then is it possible there's one clearly maximal thing? Because you said, so then how you define is...
Oh, maximally, yes, it is very clear. So this is just like identity testing. So there is some determinant which needs to vanish. Oh, so yeah, actually, it's coming in the next slide. I didn't realize we haven't talked about this yet. So is there one choice which is universally good, which will correct every error pattern that this topology can correct? The answer is always yes for every topology, right? A random code over a sufficiently large field would do the trick. Because basically what you're asking for is that a bunch of determinants, which are basically polynomials in your variable, should be non-zero. Just the Schwartz-Zippel lemma tells you that pick from a very large field and almost surely all of these polynomials will be non-zero. Right? So there exists this one setting of alphas which is as good as any other setting. If this setting corrects an error pattern, so will this. In fact, there are many such settings. A random setting is likely to do the job for you.
So these alphas are the coefficients in your pattern?
Yeah, so these are the things that you get to design. They may not be as simple. So once you start doing things like parity relations among the parity checks, right, then the meaning of alphas becomes a little fuzzy. So just say these are variables that you're allowed to choose, which will specify the code. I'll show you a couple of concrete examples of what these alphas are. Actually, we've seen concrete examples, right? So for instance here, you have these local constraints that the parity of each. Okay, we'll see an example shortly, and then it might.
Can I also, because I'm also a little confused, for this question that you said.
Your co-speaker is confused.
Yeah, I know. This is the best. Yeah.
I don't actually know this specific.
Yeah.
So clearly, as Venkat said, if you ask me if I choose all the coefficients, you give me the linear equations, but you don't give me the coefficients, right?
Yes.
The question is design the coefficients so that everything is as linearly independent
as possible.
It could be.
Yes.
Yeah. So this is like general position. So
yes.
just yeah.
Yes.
So now what you said before is going back to network coding, multicasting says just randomly choose these things in a huge field. Farzible says you're cool. Okay.
Yeah.
So now the question that is open, as far as I understand, is an explicit design of these things.
We'll come to that exactly.
The question you're asking here is different. Here you're asking, you don't even know the flows. So you're asking, why can't I just compute flows?
So he's actually giving the rest of my talk for me. So this is actually that's an even better thing. So there'll be a very smooth transition, right? So yeah, so hang on. So why do we, okay, so we have this theorem which says that, look, I don't understand what error patterns I want to correct, but random does it. Why do I need to bother to understand these error patterns? That might be a concern if you're trying for an explicit construction, because in an explicit construction, it seems like you need to understand what things you're trying to correct to prove that you're a construction. So what is the whole point of explicit constructions, right? So firstly, random over a large field will work, but how do you know that it works? Maybe you were unlucky and you happen to pick a bad pattern, and then when you deploy it, everything crashes. Okay. Now let's imagine this is not a concern, because really code lengths are short, and by running it on some cluster for days, weeks, you maybe will be able to verify it. The bigger concern, I claim, is really this large field size. Okay. So I wanted to tell you more about why this field size is so important, but that will take up a lot of time, which I don't have. So very briefly, let me just tell you that this is how encoding and decoding both will work. You have your parity check matrix that gives you some alphas. Now what you're going to do is you have these huge streams of data. You're just going to stream through this, computing this inner product, alpha 1 x1 plus alpha 2 x2 till alpha n xn. Okay? So you have to do this finite field multiplication there. That is really a bottleneck, because this is happening not just at the time of not just the time of decoding, but also when you're encoding. So you want what you'd really like is that this finite field be just a few bytes long, something like 2 bytes, 3 bytes. You'll have a lookup table of logarithms. You can speed these things up. If the field size gets really large, you basically have to do matrix vector multiplications, and this really slows you down even at encode time. Right? So big field sizes are a bottleneck. If you cannot get maximally recoverable codes over a small field, you'll use something suboptimal, but with 2-byte encoding lengths. But by the same token, you couldn't care much about explicitness. Field size is what really matters. Usually random codes are bad because we don't know how to decode them. But this is decoding from erasures. This is how it works. You lose x1. You go look at your parity check matrix and say, okay, how do I recover x1? Okay, it's this linear combination of these other machines which I still have. And now you just request the data from those machines. Who knows if they'll give it to you. Once they give it to you, you're just doing this one inner product, alpha 1 x1. x1 is alpha 1 times this thing plus that thing, and so on. So it's all about the field sizes. Whether the code is explicit or was found by a computer, it affects what this alpha 1 is, and we couldn't care less about that, right? So it's all really about the field size. So first thing you could ask, maybe there's a better analysis of the random construction. We're doing this huge union bound over all these determinants. Maybe random actually works over much smaller field lengths, field sizes. The answer to this is no. It's an emphatic no. This is a very nice result by Party and Mecca. I fear this is something that coding theorists have known for 30 odd years, and I'm going to find out right now. But here's what they prove. If you just want an MDS code, the simplest of all topologies, you're taking a k plus d minus 1 k code, you want to know when is it MDS. Well, the usual union bound argument will tell you that it's MDS for field sizes like k to the d. And they show that that's very close to tight in the sense that if your field size is something like smaller than k to the d minus 1 times some constant, there's only an exponentially small chance that a random construction is in fact MDS. Right? So random actually needs a large field size to succeed. On the other hand, we know explicit constructions, Reed-Solomon codes, where the field size is k plus d. So this is an emphatic victory for explicit constructions. The whole problem is that this Reed-Solomon construction, it's so delicate that you just, you change the problem just a little, and then we have no clue how to construct explicit codes, as I'll show you shortly. So the main motivation for finding explicit constructions is the field size here. It's all about the field size. So have I answered your question? Okay. Okay, so I'm just going to talk about this one topology now for the rest of the talk, which is maximally recoverable LRCs. You have these local constraints on the parity of each column, then you have global constraints on all remaining data symbols, and we want every puncturing that could be MDS to be MDS.
If you make your length just a little bit longer,
yeah,
then you don't need such big size.
Yes. You mean this lower bound would break for...
Yeah, if you insist of exact MDS, but if you just relax it a little, then
right.
As long as it's not binary, very quickly it becomes that any k out of n.
Right. So I think such a thing would be
anyway, I'm just saying.
Such a thing would be reasonable, but okay, so in situations like this...
You want everything tight and short.
Yeah, you need a whole lot of things to be MDS at the same time. You need exponentially, so that was for one MDS code. In these things, I need exponentially many things to be MDS altogether. So I don't know, you're right.
Exponential probability, maybe they cancel each other.
I don't know what random does for this. Even a weakening, like you're saying, as long as it doesn't blow your length up too much, ought to be reasonable. So here, it's just not clear to me what random does, and we can beat random. But thanks, it's an important point, right? Okay, so in this setting, the upper bound for random will be pretty bad because, as I said, you need a whole lot of MDS codes. We know we can get it with exponential field size, and I should also cite this other construction which would also give you maximally recoverable with exponential field size. What is the lower bound for random? Well, this is at least as hard as constructing one MDS code. So at least k to the h. So what is k and h? So k is the number of data symbols, h is the number of global parities. After puncturing, you want a k plus hk MDS code. So we do two things. We give a basic construction which gives you a field size of k to the h, right? So depending on how you want to think about random, if you want to compare yourself against the upper bound that random gives, then we are beating that comfortably. But perhaps the more reasonable thing is to compare yourself to the lower bound. We essentially meet that. We have a second construction which actually does better than random for suitable parameter settings. Okay? And these constructions are fairly simple and clean to describe. So I'm going to take about 10 minutes now to show you these constructions, and then I'll wind up. Okay? So what is the problem description? It's very simple. Maybe I have it written down here. No. Okay. So actually, can we switch off the projector? Thank you. Okay, so what is the problem that I'm trying to solve? I want to think of my symbols as arranged in an r plus 1 times n over r plus 1 grid. I want a code which has two kinds of equations. One is local parity checks on the column, which say summation xij, I goes from 1 through r plus 1 is equal to 0 for all columns. And then I want H global constraints, right, which are of the form summation alpha I comma j, sorry, as alpha I j k xij is equal to 0 for k. Have I used k already? I have, so let me use a different alphabet. Let's call this L. For L in H. So these are the two kinds of equations that I have, and I want the code to have the property that puncturing one entry per column leaves me with an MDS code. So why did I insist these coefficients are 1? It's not important. You could rescale the symbols or something like that. So let's just say this is the problem that we want to solve. Okay? So the trouble with this is that you don't want one MDS code. You want a whole bunch of MDS codes. You want a whole bunch of codes to be MDS at the same time. Right? So what is the basic construction of MDS codes that we're going to use? It's going to be a slightly inefficient version of Reed-Solomon codes. Okay? So let me just present to you now a family of codes which are based on linearized polynomials. They're more inefficient than Reed-Solomon, but they have other nice properties. Okay. So let's just consider codes of some length m, which I will relate to n later. And we want H parity checks. We're going to choose them of the following shape. Alpha, alpha 1 squared, alpha 1 to the 4th, alpha 1 to the 2 to the h minus 1. So H of them. And you have m elements, alpha 1 through alpha m here. So this is my parity check matrix for some code on m elements which has H parity check equations. When is a code like this MDS? This is basically asking if I have H such elements, when is the determinant non-zero? So very clean characterization of that. This code is MDS if alpha 1 through alpha m are H-wise independent over F2. So alpha 1 through alpha m are coming from some extension field of F2. You can think of them as vectors over F2. This says that any H subset of these guys should be linearly independent over F2. The proof is exactly what you think. If you just take the square determinant where you have H of these alphas, and you say, when is this determinant non-singular? It's non-singular exactly when alpha 1 through alpha h are linearly independent over F2. It's obvious that if they're linearly dependent, then by linearity, you'll get a relation between the columns of the matrix. That is also a sufficient condition. If they're independent, then the determinant is non-zero. So now what we want to construct an MDS code is a collection of vectors alpha 1 through alpha m, such that any H subset is linearly independent over F2. Minimizing the field size amounts to minimizing the dimension in which these vectors live. So here's the problem now. Come up with these m vectors, which are H-wise linearly independent, and do it in the smallest dimension possible. This sounds like a very nice linear algebra problem, and it is the problem of constructing good binary error correcting codes. Because take the parity check matrix of any binary code which has length m and minimum distance h plus 1. Okay? So take a binary code, binary linear code of length m and min distance h plus 1. Okay? So now look at its columns. Any h of these columns better be linearly independent over F2, otherwise you'd get a code bird which has weight only h. So now, what is the dimension in which they live? This is exactly the number of parity checks you have to throw in order to get a code of distance h. Naively, it would be h log m, but by the BCH construction, you can get something like h over 2 log m. Right? And it's because of this factor of 2 that you'll get alphabet size. So you can take alpha i's belonging to FQ, where Q is something like m to the h over 2. Right? So we're doing better than the random construction using BCH. All right. So now these are the kinds of codes that are going to show up in our construction of maximally recoverable LRCs. So again, the plan is exactly the same. These parity check matrices are going to have this shape, alpha ij raised to 2 to the L minus 1, right? So what I do is that I assign some alpha ij to each symbol here. And then I say that my global parity checks are exactly of this shape. You take your alpha, raise it to various powers of 2. So alpha is the first parity check, alpha squared for the second, alpha to the fourth for the third, and so on and so forth. All right. And I claim that by suitably choosing the alpha i's, we'll be able to get the stronger property. So let's see that this is indeed true. So let's imagine now. So sorry, is the description of the code clear to everyone? So now let's imagine that we have a puncturing, 1 per column. And just to make my notation simple, let's consider the case where the puncturings all happen in the last row. You'll see exactly that it's only a change of notation. Right? So all these symbols x, I, r plus 1 are gone. We want to argue that we are left now with an MDS code. How do you do that? Well, you just eliminate xr plus 1 using, from each column, you eliminate the last symbol by writing it as the sum of the other symbols for all g. Okay. So now we've used this to eliminate the missing symbols. Let's plug this back into this equation. So okay, this was a summation over I, j. So let me tell you what's going to happen, and we'll see if it actually happens. The effect of eliminating this last row is going to be that all these numbers here, they get shifted by that alpha. You take all the numbers in each column, add alpha r plus 1, 1 to them. Take all these coefficients in the jth column, you add this to them, and the code you get is exactly this kind of code with these constants for each entry. Right? So let's see why this is the case. I'm taking this equation, I'm putting it into this thing here, and I'm tempted to write on the wall because it will be most convenient, but maybe I should write down here. Right? So I have this summation over j, summation over I going from 1 through r plus 1 of this quantity, where what I do is I write it now as a summation of I going from 1 through r, alpha ij, 2 to the L minus 1, xij, plus alpha r plus 1, j times summation xi, I going from 1 through r plus 1, raised to the power 2 to the L minus 1. So basically what happens is that this thing, I can add it to each and everything here and rewrite this as nothing but summation of this xij. Okay? And then by linearity, I can take the 2 to the L minus 1 out and say that. Okay. So just using simple linearity, the effect of this is to shift all these alphas by the same element from the bottom row. Okay. So now we're going to use this fact. We want this code to be MDS. So we came up with this new table of numbers where every element was shifted by r plus 1, g. Okay. The same shift was applied to elements in a column. We want this collection to be h-wise independent. So what is a linear combination of h elements of this kind? It is a sum of at most 2h of the alpha i's, and moreover, it's a non-zero sum. Yeah? So why is it non-zero? The only possibility for cancellation comes from multiple elements in the same column, because they all have the second element which is the same. So if I add an even number of things, the second thing disappears. If I add an odd number of things, then it's hanging around there. But these first elements, they cannot cancel out, right? So sum of h alphas of the form alpha ij plus alpha r plus 1, j equals, so a non-trivial sum equals a sum of at most 2H alpha ij's. Right? So now if we want the stronger property from our construction, we just need to choose the alphas to be 2H-wise independent instead of H-wise independent. Again, BCH will do this for us. You know, the factor of 2 that extra factor of 2 that we got here will be cancelled by BCH. And you can do this over a field size FQ, where Q is equal to M to the, sorry, it's M is now something like K. Field size K to the H. Maybe I did that a bit briskly, so let me just say it again. If you just wanted the MDS property, it's sufficient that you have 2HY. You just have H-wise independence. To get the stronger property, you just don't need that the alphas themselves are linearly independent. You're going to consider various shifts of the alphas, where you take one entry from each column, and you shift everything in that column by that entry. This is the new collection of things that you want to be H-wise independent. One way to do this is to choose the alphas themselves to be 2H-wise independent. That gives you a field size something like K to the H. I was going to tell you a bit more about the second construction, but maybe since lunch is in the offing, I'll skip that and just wind up with some nice open questions, I think. Oh, can we have the projector? Thank you.
While you're waiting for that to come out, so it seems related to this other construction with linearized polynomials, but here it's better because you have h in the exponent instead of n.
Oh yes, yes, yes. So I'm still thinking about this setting where h is small compared to the other parameters. So k to the h in that regime is better. Right? And maybe, yeah. So yeah, I think that's the only. I mean, also. Maybe if you want to think of large H, you don't use BCH, you use some other binary linear code, then I don't know how they compare. It's a fairly general template for constructing a code. And I should mention that in some cases, BCH is not, for some specific distances, BCH is not the best construction. No? And there are improvements there, and then you get things that, even by this construction, I think you'll get things that clearly beat K to the H. Okay. So we got something like K to the H. There is no reason that you cannot get these maximally recoverable LRCs over linear field size like Reed-Solomon, and maybe some clever modification of Reed-Solomon will do the trick for you. So it's an interesting question whether you can construct such LRCs over linear size field. We understand nothing about a tensor code when it's maximally recoverable. I think it's a very nice question. We'd like explicit constructions. To do that, it feels like you need to understand what kind of error patterns we are trying to correct in the first place. And this question of, does this notion of maximal recoverability require large fields? Could it be that there are some natural topologies? For a lower bound, maybe we are even happy with relaxing the notion of what is a natural topology. But are there natural topologies over which you can only get maximally recoverable codes by taking the field size to be extremely large, which is exponential in the length? Or we don't know of any example where you require a non-trivial alphabet size superlinear, right? So proving a lower bound also would be very interesting. All right. So let me just, so I'm done now. I'm going to leave you to Alex from tomorrow onwards. But before I wind up, I just wanted to say a few thank yous. Thanks to the Simons Institute for organizing this wonderful semester, and to David and Venkat for inviting me to give this talk. A lot of what I've said today is, it's basically based on work in collaboration with people both in Azure Storage and MSR, especially Sergey, who is here today. So I'd like to mention Brad Calder, Cheng Huang, Aaron Ogus, Hussein Simichi, and Sergey. And lastly, this was work done at MSR Silicon Valley, a fantastic lab, which, as you know, was closed a few months back. And a lot of our ideas were influenced by our colleagues there. So, I'd like to thank them in absentia.
Any questions?
Yeah.
some nice survey about all these results, like in one place where we can read it?
No. The slides are the best that you know, I thought about this. I think it's too early for a survey. There's lots of...
11 there is, but since then there's been a lot of...
Yeah, I mean, oh, sorry. Regenerating codes, there are maybe more than one very good surveys around.
They're not updated also.
Fair enough, okay.
So up to 2011 or 12 there is, but this is 2014 stuff.
I mean, if you want a good survey, think about regenerating codes.
So which of this, if anything, has been actually implemented and is in production?
Oh, good, yeah. So these actually, LRCs are being implemented in Azure. The codes which we use are very similar to this topology. It's a baby version of this topology. They really cared about upgrades and, you know, having good distance after upgrades. So the precise property they wanted was puncturing should leave me with an MDS code. This has been in production in Azure since 2012. In fact, this was the motivation for me and Sergey to prove this lower bound to see whether the codes we suggested were anything close to optimal. Since then, even other things like Windows, you know, I don't know how many people use Windows, but there's something called Windows storage spaces where if you want to set up a cluster of 60 machines, they'll give you various kinds of erasure coding options. Reed-Solomon is one of them. LRCs are other of them. I also believe we've published everything we've done. I believe these codes are being used by other companies. You know, but this is just my speculation. I don't want to say anything. I think there's publicly available things which say that the cost savings from moving to LRC as opposed to Reed-Solomon are of the orders of hundreds of millions of dollars.
So is in this construction that you say you use, the local parities, the gray ones are
So yeah, no, so actually...
Is this a tensor, what you said before, as a tensor construction or
No, so I'm using the same picture because I'm lazy, right? So when I talk about LRCs, these gray things depend on everything. When I talk about tensors, they only depend on the row. And then it's the same code used in every row so that you have the tensor product structure. In both cases, you get to pick only H equations. In the former, they can depend on everything. In the latter, they only depend on things in the row. So this is what our general definition allows you to do. It says these things depend on these symbols. You decide how.
The tensor is just that it's the same linear equation.
It's the same code in every row, and the column has a parity check equation.
I see. That's the extra constraint.
It's a very different thing, right? Because if you look at the other, sorry, I'm talking about LRCs here. In LRCs, you won't see a non-trivial code within each row, right? Because these other constraints are global. In a tensor, each row is also a code word. It's an MDS code. Right? So they are very different. I shouldn't have used the same picture. I apologize for that. Oh, it's going to take a long time. Yeah. So here, this is a code word. Okay. Every row supports a code word. In the LRC case, you know, the rows need not have any local structure.
So, do you have any conjecture on when the tensor thing is MR?
Not a conjecture which I can state succinctly in the time we have before lunch. Why don't you ask Sergey?
Before lunch is negative.
Yeah, exactly.
Yes, and then some special cases where you can actually prove, but not a general case, especially not a general case if you allow multiple parities per column.
So let me mention that I think, maybe Sergey thinks this way too, that this is a fantastic candidate for a lower bound of superlinear size. You can't get these things over.
But even for that...
Oh, wait. No, not this. Some variant of this. We'll talk later. It's clearly time for lunch now.
So on that note, let's thank Parikshit again for a great 2 hours.